This is the 3-minute video explaining my project of the breaker graph. So right here we see all the materials I used to build it, like the wires, clothes peg, the lolly sticks, hot glue gun, hot glue sticks, and all the other servo motors and other wires I used to create the project. And right here is where we see my final product, having a shoulder motor, an elbow motor, and a pen lifting motor that lifts the pen off the paper. I also added some weights and paper inside of the weights to minimize the movement and the shake of the pen, and also to weigh it down when the pen lifting motor lets the pen down. I also added a board and a dictionary to keep the pen from moving. And each of these jumper wires connect the servo motors to its power, to its ground, and also to its corresponding signal from the Raspberry Pi. Now let's look at my engineering notebook. So starting off, I got my materials, my dad helped me buy it, and I marked the lolly sticks with 8 centimeters, and that's where I drilled holes in. And using the helpful video from the GitHub, I was able to build and hot glue all the small parts of the lolly sticks, all the servo motors to the boards and also the lolly sticks, and as well as the clothes pegs. So those went directly in, and this is me screwing in the last bolt to the pen lifting motor. And after that, the prototype was complete. Remember, this is not the final product. And also, spoiler alert, one of the servo motor's wires did not go into the correct signal. I'll explain that later. So, with massive confidence, I started off trying to draw something. But before I did, however, I needed to understand what a servo motor was. So I saw a picture on YouTube explaining what a servo motor did. And because of the 50 hertz, each frame is 20 milliseconds. And the pulses between 0.9 milliseconds and 2.1 milliseconds determine which position the servo motor will turn. So now that I sort of understand how a servo motor works and what a servo motor is, I can start calibrating it. So my first observation while trying to make the servo motor move was that the elbow motor kept jerking around randomly, as you can see from the lines. It jerked back and forth many times. And I also realized that the pen lifting motor was extremely slow. And that didn't really make much sense. So I changed the pen lifting motor and the elbow motor signals around, and I also added some weights to the pen because the pen sometimes lifted off the paper. And that led to the tape being the weight, and also the pen lifting motor signals being swapped around. And then I started trying to draw the Africa map. As we can see, that's kind of squished. So I used the calibration on the GitHub and changed the default value to 1500 and 1500 to correspond with the 90 degree and negative 90 degree angles. But it turned out it made the Africa map even more squished. So I guess I misinterpreted it. So instead of using the default value, I inputted my own value of 1440 and 1400. That made the 90 degree and negative 90 degree. So now I was ready to draw the Africa map. And the starting position was a little slanted, but the Africa map turned out quite well. And changing the starting position using the BG set angles, I was able to reset it, and it ended up with this picture. And the lines were pretty crooked because of the tape being too wide and it having the ability to switch around. So I swapped to a smaller weight so it wouldn't shake the pen around. Like right here. And then I started calibrating the pen lifting motor. I used the BG pen RPI set servo pulse width, and I used that command to calibrate the pen lifting motor. At 18,2000, that's when the pen lifting motor faces all the way down and lifts the pen off the paper. And at the default value of 1500, that's when the pen is let down to draw on the paper, as you can see in this picture. And so after doing all of that, I was ready for the advanced calibration. So I printed out the 20 splines of 18 degree angles for each protractor. I tested out the shoulder motor and changed the default values into my own pulse widths. And I also tested out the elbow motor and inputted my own pulse widths. And so in the end, this is the Mona Lisa before I did the calibrations. This is Mona Lisa after, USA before, USA after. The Kanagawa wave before and the Kanagawa wave after. And that is how I calibrated and built my brachiograph.